got my applause at the beginning. This is great. Well, thanks very much for having me. As Nick said, I'm Allie Gilmore. I work at a company called Ayasdi. We're a Series C startup out in Menlo Park, and we do topological data analysis. So we were actually founded out of the Stanford math department by a mathematician, and that's my background as well. I come out of topology. I was a postdoc doing topology a year and like 4 days ago. And I'm very happy to be here instead. So my goal today is to convince you to think of shape as one of the fundamental organizing principles of data analysis, and also then to convince you that topology is the right way to study that shape. So the premise is simple. It's that data has shape, and that shape carries its meaning. And whether or not you think about data analysis in this way now, in fact, I claim that you already know this, and you use this fact anytime that you do any standard data analytics. So what does that mean? Well, say you're fitting a linear regression. You assume that your data is sampled, well, it's probably not sampled. You'd assume that your data is distributed somewhere roughly near a hyperplane in space or a line if we're doing a scatter plot. Right? If your data does not meet that assumption and it's not just somewhere near a line, your linear model isn't going to work very well. So it's the shape that drives the meaning of that analytical method and is the underlying fundamental assumption. If your data is near a line, this is a great method. Right? It gives you a compressed representation of that data. You've gone from a point cloud down to a couple of numbers, the coefficients in your model. And it helps you understand in a very precise way what the relationship is between the various features in your data. Of course, if your data is not aligned, maybe it's something else, right? Maybe it falls into a couple of discrete clusters. Again, if you know that your shape falls into a couple of different clusters, then you can apply a clustering algorithm, and that will work pretty well. You may also need to know how many clusters it falls into, but that depends on the details of your algorithm, right? If your data does not fall into clusters, your clustering algorithm will probably produce nonsense. So again, the shape of the data, whether or not it actually splits into disparate clusters, determines the success of your algorithm, and that is your underlying analytical assumption. But there are lots of things that could be happening besides lines and clusters, or even besides curves and clusters. Maybe your data is distributed like a circle. Now, there are methods for handling this kind of data as well. Oh, and this kind of thing does happen, right? If you've ever dealt with time series data, this would be the kind of pattern you would see with recurring phenomenon. So this is a real situation, and there are methods for dealing with this, for saying that data looks like a circle. But they're a little more obscure than the linear regression or the clustering. And then what if your data looks like this? This is also a perfectly reasonable thing that can happen with data, right? You see this kind of a situation where there's a central core of common behavior, the standard trend, the usual thing, right? And you see then different disparate ways of deviating from that common behavior. It's sort of like clusters, but it's not actually clusters because there's this common core holding it together, and it's certainly not a line, and it's not a circle. And so any of these standard algorithms that's based on the assumption that your data has one of these shapes is going to fall down in this case. But this is a really reasonable case. So what you start to see out of this is that in fact what you have is a suite of methods for dealing with different individual shapes, assuming that you pretty much know what that shape is going on. But you usually don't know what shape your data has up front, and usually your data does not have one shape. It has a whole combination. So what you need is not a method for dealing with each independent kind of shape, but a way of understanding shape itself from the beginning without knowing in advance what it is. So in mathematics, there are two ways of studying shape. There's geometry and topology. And each of these has its place, but let's think about which one would be more useful for data analysis. So geometry depends on a metric. Its fundamental notion of shape is based on a metric or on distances between points. So in geometry, you will not be surprised to hear, the circle, the ellipse, and the square are all different, right? That's because in geometry, two shapes are called the same if you can map from one to the other while preserving all the distances between all of the points. You cannot get from the circle to the ellipse or from the circle to the square with a map like that. You can do all the standard things you're allowed to do in high school Euclidean geometry, right? You can rotate things. That's fine. The ellipse doesn't change its shape when I rotate it. And you can translate things. That's fine too. The square's shape is the same no matter where I put it on the screen. So that's geometry. Topology is based on a looser notion of shape, a looser notion of equivalence. And that notion is around the idea of locality. So locality means we care about which points are nearby each other, not specifically about the absolute distances between points, but about which ones are close together and which ones are far apart, relatively speaking. And that means that in topology, the circle, the ellipse, and the square are all the same. That's because you can take the circle and you can stretch it, or you can push it back, and that doesn't change which points are relatively close together and which points are relatively far apart from each other. So that doesn't change what shape you have. You can take the square and you can round off its corners and get a circle. That doesn't change the neighborhood of each point. It doesn't change which other points are near it. So topologically, those are the same shape. So this looser notion of equivalence, what it cares about is not distances, but about continuous deformations. Anything that you can do to change one shape into another by sort of pushing, pulling, stretching, rotating, and translating are all still fine, just as long as you don't tear or puncture, you have the same shape. So now, which of these notions makes more sense for data analysis? Well, the question here maybe depends a bit on if you're a scientist or an industry practitioner. If you know the scale of your data, you know it really well and you really believe it, and you believe the relative scale of one feature against another, and you trust that you have measured these things carefully and you have an expectation about the functional form about how they're related, then maybe geometry is the right tool for you, because then you know something about absolute distances. I usually work with healthcare data. I usually don't collect it myself. It comes to me. It comes to me with the wrong coordinates. It comes to me noisy. It comes to me on a ton of different scales, because we're measuring, over here the patient's heart rate, and over here how much the hospital billed to the insurance company. And so I don't believe really anything about the scale that I get my features on. And I certainly don't believe anything about the relative scales between those features or the functional form. So topology is a more natural choice in that kind of a setting. So what does it mean to use topology to study the shape of your data? There are actually all kinds of answers to this question. There's a whole field of mathematics called topological data analysis. But there's one thing in particular that we do well at Ayasdi, which is the following algorithm. So this is obviously a toy example. Scatter plot data of a circle. And all we want to do is capture exactly what we can all see, which is that this data is a circle. Okay? Don't worry about the colors for the moment. It's just noisily sampled from a circle. So here's what we do. We consider a real valued function on this data set. That function we call a lens, but it's any real valued function. In this case, we're just going to map each point in the data set to its y coordinate. Okay, so it's a projection onto the y coordinate. That's a real valued function. In the image of that function, we produce bins, overlapping bins, or topologically, this is an open cover of the image of the space of the function. So these blue bins, like this, overlap across the image. Then we ask which data points were mapped into each of the bins. In other words, we take the inverse image of the bins under this function. Split the data points out like that, so that now you can see it was the top arc of the circle that went into the top bin. It was this top middle piece that went into the middle top bin. It was this next slice that went into the middle bottom bin, and it was the bottom arc that went into that bottom bin. Okay. There was overlap. I'm going to just play that again. There was overlap between the bins, so some data points ended up in more than one place. So now what we do is within each bin, you run your favorite clustering algorithm. When you do that in the top bin, this one arc, you see one cluster. In the two middle bins, you see two distinct pieces, two clusters. And we're representing the clusters right now as dots on the right-hand side, but what we're going to construct is a graph, a set of nodes and edges. So in the second from the bottom bin, again, we see two clusters, and in the bottom bin, we see just one. So you represent the results of this local clustering technique with these nodes of a graph. And then you keep track of when data points ended up in more than one cluster. So the orange points over here, they ended up both in the top cluster and in this left-hand middle cluster. So we record that with this edge here. And similarly, there were some orange points here that ended up both in the top cluster and in this right-hand middle cluster. Record that with this edge. Likewise, these green points, they were in this cluster as well as this one. Track that here. And as you do that, what you're doing, right, is you're clustering in small regions of the data space, and then you're keeping track of how those clusters belonged together. And that captures the shape. In this case, it captures the fact that you had a loop. A couple things to notice about this. So first, the output is a graph. It's a combinatorial object. It's a compressed representation of your data. So just like in linear regression, you take this huge cloud of data points, you smash it down into a couple of coefficients that describe your model. In this case, your output object is not numbers or a function, it's a simplicial complex, or the way I described it, it's a graph. The algorithm generalizes in a pretty natural way to give you a simplicial complex. It's a combinatorial object that you can work with, that you can represent on a two-dimensional screen, and that is much more tractable than the original data space. The second thing to notice is that it's a topological capturing of that shape. So if our original data points had been sampled from an ellipse, you still would have gotten a graph with one loop. If our original data points had been sampled from a square, you still would have gotten a graph with one loop. It's capturing that fundamental topological property. It's not really capturing the geometric properties. This method captures complex shapes as well as it captures simple ones. So on the left-hand side here, this is a standard adversarial example for a lot of machine learning problems. It's one that this method handles very easily. So you do the exact same algorithm where you project onto the y-coordinate. You look back at the inverse image of bins in that projection. You do clustering within those inverse images, and you keep track with nodes and edges the result of that clustering procedure. You get a red piece and a blue piece. Right? So the algorithm sees that topologically, there's only two things happening in this graph. There is a red thing. All of the red points are connected to all of the red points. And there is a blue thing. All of the blue parts are close to all of the blue parts. And it separates those out very easily without worrying about it. Doesn't care about the fact that they were embedded in some complex spirally way. So this is what that looks like when you apply it to real data. You get much bigger graphs. But these graphs, their large-scale properties still capture the sort of fundamental topological features of your data set. So when you look at a graph like that, remember what the algorithm does is keeps track of this sort of local clustering method. And so the nodes in the graph correspond to those clusters. So the nodes are groups of similar data points. And there are edges between two nodes whenever there was overlap between the corresponding clusters, meaning there are edges between similar nodes. Now again, it's a graph, a network, not a plot, so it's not important where the nodes and edges are on the screen. It's just important what's connected to what. Okay, so that's nice. We can use this to capture shape. Where this really starts to get interesting is when you incorporate traditional methods as well. So start with a baby step. You can incorporate PCA very nicely into this technique. So this is an example of the output of a PCA algorithm. This is a plot of a data set projected onto its first two PCA coordinates. And what you see out of this PCA plot is that this data set appears to have three clusters. And in fact, if you measure the variance captured by PCA in this example, you will get 98.4%. So you would probably run this and say, I'm good. there are 3 clusters in this data. The way that you incorporate this with the topological approach is as follows. Instead of using projection as your real valued function, you use the PCA coordinates as the real valued function that controls where the bins come from. So what does that mean? So you have these first 2 PCA coordinates that are plotted here. You divide this PCA plot up into overlapping regions. So a circle here, an overlapping circle here, an overlapping circle here. And now those regions, those overlapping regions, are an open cover of this space. They're the equivalent of the bins that you saw on the real line. So now in each of those PCA regions, you look at the inverse image of the function that projected down to this PCA plane. So you go back to the original data set and you say, which points in my original data set ended up in this part of the PCA plane? Look at those points, run a clustering algorithm, see how many clusters you get, represent those with nodes in a graph, represent the overlap between them with edges, and you get this. So there are 4 clusters in this data set. What happened? Well, if you picture the PCA plane, right? In the PCA plane, there were 3 clusters, but we projected down onto that plane. So there was some projection loss. We know that can happen. I mean, that's fine. But when we capture 98.4% of the variance, we usually don't worry about that too much. What happened here was that there were 3 clusters, and there was another cluster sitting just on top of one of them in a direction orthogonal to the first 2 PCA coordinates, but not at a distance far enough to screw up the variance captured measure, right? The scale of this separation was much smaller than the scale of the separation between the clusters. But there were absolutely 4 distinct clusters in this data set. And when you incorporate the traditional method along with the topological approach, you can see that. So we also do this in real cases. I'm a mathematician, so I love toy examples, but we also do this with a lot of real data. We mostly work, in fact, with customers in healthcare and finance. But the example that I find really compelling actually comes from a collaborator of ours at Stanford. His name is David Schneider, and he works in the Stanford Microbiology and Immunology Department. So the data sets that he studies have to do with infectious disease and with what health looks like, what sickness looks like, and how people move between them. So we'll do something like take a mouse, infect it with the flu, and then take measures from that mouse over different time points, maybe measure the transcriptome, so the proteins that are expressed in that mouse. Maybe measure immune system function, the cytokines. Maybe measure clinical data, maybe not about the mouse, maybe about a person, like temperature and blood pressure and that sort of thing. And measure those things for many patients over many timestamps. Those are the data points in this analysis. And then what you'd like to understand is what are the characteristic states of health and sickness and in between. And the traditional way that people thought about this is that there's health and there's sickness and there's a continuum of states in between. And what our collaborators saw across many different data sets, collected in different ways, different species, and different types of data, is that in fact it's not health and sickness and some stuff in between. There's a path from health to sickness, and there's a path from sickness to health, and they're different. And with the topological approach, that's the difference between a line and a circle. It's absolutely clear that those data sets have different shapes. And the fact that it's a circle and not a line carries a lot of significant meaning about the problem that you're studying. So this is a result that he saw replicated across a number of different data sets, and it's a fundamentally different way of understanding this problem. So, as I said, we do a lot of work in healthcare and finance as well. I have a number of other examples I'd love to talk about within the limits of what I'm allowed to talk about. And please come find me if you have any interest in topology or topology and data analysis or Ayasdi's work. Thanks very much.